So, thank you. I will talk a bit about TCP, but I don't know much about TCP. So who of you is kind of TCP knowledgeable here, knowing things inside out TCP? One, two, some people having implemented TCP before as a kind of a hobby project, that one. Okay, good. But I guess you all have used TCP. Hands up who have used TCP. Ah, okay. You can hardly avoid using TCP. It's one of those kind of protocols that you do on a daily basis. So this talk will be about testing an open source Erlang TCP IP stack. And the title, when I sent off the talk, was performance and testing, but we never got to the performance part of it yet. But so I will only talk about the testing part. This is joint work with first and for all, the writer of this open source TCP IP stack, Xavier Paris, from the Spanish University in University of A Coruna. He was kind of the originator of this work. And then Alistair, sitting there, got him that far that he open sourced it. And Otolonetworks is then using this stack for building some stuff. And the picture under there in the boat, that's talking about really, really bad working circumstances. So this guy is sitting in this very small boat in this horrible place in the world, far away from everything, French Polynesia, and he just has to work there on things like TCP/IP. So if you can help them, this is the main message of the message. If you can help this poor guy, then please do so, right, by working on this open source stack, because he really needs that. So then the guy doing all the testing and writing this model, that's of course Ulf Norell from QuickCheck, and I may present it. So that's how things work. Okay, TCP/IP. You all use it. It's a transaction control protocol on top of the internet protocol. So TCP makes sure that the packets you send over the internet are reliable, that there's a sequence number, that if they are arriving in a different order than you actually would expect, they put them in order again, such that you can experience the internet as a consistent thing that is reliable. That's the whole idea of it. There's some error checking, some parity stuff, all that kind of things, just to make the packets that arrive to your computer work as they should. So this is normally done in the kind of kernel of your operating system. If you use a Unix version or Linux version, there's a TCP stack in the kernel, there's a TCP stack in Microsoft, and there's a TCP stack in any other esoteric kind of operating system, because those things have to talk to each other. So not many people will implement their own TCP/IP implementation, because why would you do so? You always have one already, and that's probably more faster and more complete than the one you have yourself. So that's why it's nice if people at university start to do that, and there was actually a purpose of doing that. But now we have an open source Erlang implemented TCP/IP stack. So it's completely natively Erlang, and the good thing is that it's highly concurrent. In order to kind of experiment with lots of concurrency, he used this stack. But also, it's a user level stack, so you can actually change that stack, and that's kind of cool. You can do all kind of things. You can use it for inserting strange packets into your network, or use it to hack yourself into systems that are not that well secured, and things like that. So that's very good to use that kind of implementations. You can use it yourself, and you can contribute to it. It doesn't have many features, so it is kind of plain TCP, and TCP has, over the years, got lots of additions and features, and it's not all implemented, but feel free to do so. So our goal now was to use that. Well, Otolonetworks wants to use this TCP/IP stack for products, and were asking us to test it with QuickCheck. And then the question is, okay, how do you test such a thing? Well, how does it look like? This is how it looks like. It's actually just a state machine. You're all very familiar with state machines, I guess. Have you? State machines, okay? Yep, you've all seen state machines before. So state machines are a very nice way of specifying how things work. And this is the state machine of TCP. And it doesn't look that complex if you look at this. The complexity comes from lots of options in the packets and things like that, but there's much more below. This is the control flow. And this picture actually presents two parts of the TCP protocol at the same time. So you have your server and your client. And the server normally can start a listen socket. So that's the thing that if you start your web browser, then there's on port 80, there's a listen socket. And then there's the application, your browser, that connects to that listen socket. So what the listen socket is doing is waiting until someone says, hey, I want to talk to you, and the someone is the browser. And that browser then sends a SYN message, SYN from synchronize, I guess. This one receives that SYN message and sends a SYN ACK back to the browser and gets into the SYN received state. So, okay, I got my SYN received, someone wants to talk to me, and that's it. I'm just going through this a little bit. So this one is then this SYN received state, and then the SYN send guy, this browser says, oh, I got my SYN ACK from here, I acknowledge that, and I'm in established. And this acknowledgement is matching up with this one, and this one is established as well, and now you have a connection. Now those two can talk to each other until one of them gets enough of the other and says, okay, I terminate the connection. And then they send a final message. They're very polite, so they send a final, gets a final fin message, send an acknowledgement, oh, I got that, then waits to get another fin message, and then says, okay, I acknowledge that as well, and I'm back again. Or it goes that way, where it's a bit more complicated to say, hey, I want to stop. Yes, okay, I heard you want to stop. I want to stop as well. That's it. So this is the protocol. It doesn't look very complex, right? Should be testable. So how would the test look like? And now we get into the trouble. The test looks like calling some API functions. But there are not that many API functions. So a typical manually written test would look like start a socket. Another way, start a listening process. And then, well, close the socket again. That's the test. Or if you are lucky, you can actually also start a browser that talks to that listen socket. But that's about it, what you can do. You are immediately in established. That's my point. So the API is very, very limited in the sense that you have a listen, a connect, and a close operation. There's not much more there is. Nevertheless, the protocol looks difficult enough to think that with those three operations, you probably test everything, but you have to get it in all the states. How do you do that? And that's very unclear how to do that. Well, running it a lot of times might be the way to do that. But that's not really kind of satisfactory. Okay, I run 1 million tests. I might have hit all those kind of possible states. Probably not. So that's not very satisfactory. So the API is typically some kind of those APIs where you cannot really reach inside the state machine that you want to test. So although this talk is about TCP, it holds for many more systems that it's difficult sometimes to look inside the system and make sure that you have seen all the difficult states that you cannot reach directly from your API. The other thing is that there might be some race conditions occurring that absolutely need testing. Race conditions are typically the things that you might see here, although you might not see them in practice. They may pop up now and then. And there's also other things that may appear. Message loss. Some kind of acknowledged message may get lost and never arrive. Does the protocol still kind of behave correctly with the timeout and things like that? So you need a lot of testing for this. One of those things that may happen is that both sides want to close the connection at the same time. This could happen, right? Both want to close at the same time. How is this handled? Can we test that? They close at the same time, they get the acknowledgements, and then actually they go to back to the state they were in. That's not very easy to provoke. So if things are really, really difficult in testing, right, if they're really, really difficult, what is the kind of industry best practice of solving that? Hard to test systems, how are they tested normally? What is the approach? That's one thing. Ship it. Don't write tests. Because if it's very hard, don't bother doing it, right? So that's the kind of the normal way of doing it. And that's completely in our philosophy as well. If something is very, very hard to do, like writing tests, don't do it. We go one step further. We say, well, if you don't write the tests, we want to generate them, right? So we generate the tests. And that's what QuickCheck is kind of doing for us. So we generate tests from the specification. And the specification you've seen, this is the state machine, and we want to generate automatically tests that go through all the possible states in that state machine. And for that, we need a kind of a tool, and that tool is QuickCheck. And I've presented it many, many times, but probably not all of you have seen it. So we'll give a little demo here on how that works, okay? And then I will go back to TCPIP to show how it could work in that place. So let's look at a very simple example that most of you will have seen. That's the process registry. process registration, sorry, not process registration, a process registration in Erlang. Who is not familiar with the process registration in Erlang? One, okay. So process registration is as follows. You have lots of different processes. You spawn a process, and then you can give that process a name. And the next time you want to send a message to the process, you can use the name of the process to send the message to. That's the whole idea of the process registration. So there's 3 basically API calls that you can do. You can register a certain process identifier under a certain name, which should be an atom, or you can ask, where is this atom? And you get the process identifier back, and you can send a message to that atom. So it's a kind of global in the node you are, store for process names. And then there's also an unregister, but I will not show in the demo how we do the unregister. I just want to focus on the register and the where is, just to show you how that would look like if you want to test that API. So you can imagine that if you have 3 calls in your operation, or even 2 calls, you can have lots of different combinations of test cases. So if you want to test the registration, you have to write test cases where register and where is are occurring in all kind of ways. So I think I can now jump to that demo. So the kind of test cases I want to generate are those. Here's an example of a test case that I want to generate. This is one test case, right? I spawn a few processes, and they are, you should read it like this. This is a symbolic representation of a test case. It's a call to the register EQC spawn function, and it is bound to the variable 1. And the result of this spawn is bound to variable 2. And the result of this spawn is bound to variable 3. And then I can do a register, or where is, actually, I can do where is A, and I can do a register of variable 1 under the name D, and a register of variable 3 under the name A. So this process and that process are now registered, right? And this is a test case. And you can see it's kind of a bulky test case, and it's automatically generated. I can do a few more. So let's show you how to do that. I call my model and say, give me some tests, and then I generated 10 different test cases here. And that are all completely different. Some of them are shorter, some of them are longer, and they all have this where is and register in there. So now you probably wonder what is needed to generate those test cases, and how can we run them? First, I will show you what is needed. What is needed is a state machine specification. So you have to specify how you can make your test cases. And that state machine is specified here. So you have some headers where you introduce your state machine formalism, and then there is a state. So my model has a certain state telling me what I think the system state of that moment is. And in my state, I keep track of all the process identifiers I have spawned and all the registered processes I know. There might be more, but that I know of. And then I have a kind of fixed set of names that I can give to processes. I call my processes A, B, C, D. Right? I could have chosen other names. I could have chosen more names. I could have chosen very strange names. Nowadays, I can choose Unicode names, right? It's fantastic. You can try that as well. We did. So that you can do all that kind of things, but I want to have a reasonable possibility that the names kind of are the same. So that's why I choose only 4 names, because in a long test case, you will then use the name several times, probably. And that's when the test case is really interesting. So then I have to have data generators for reproducing some random data. And I have a name generator which says, well, give me a random name out of this set, and give me a random pit, which is taking from the pits in the state a random number. So that's all. And initially, my state is empty, as you can see in the last 2 lines here, or scrolling up now. So initially, my state is empty. So now I'm going to fill my state by creating test cases. So each a test case is a number of API calls. For each API call that I want in my test, I need to specify something. So here I specify for the spawn command, I specify what are the random arguments when calling a spawn function. There are no random arguments, fine. What is the spawn function doing? Well, it's called Erlang spawn, and it sleeps for 5 seconds. 5 seconds is eternity in the life of the test case. No test case will run for 5 seconds. I have to make it extremely long to run it for 5 seconds. So this says, I will survive my test case, and then I will silently die, so I don't have to clean up and kill all the processes. So that's fine. The next state, now it's important. Now I'm going to update the state of my system. I add the process identifier that I just created to the state of my system, and that's in the next state function. So this is how that works. You specify step by step what the thing is doing. For the register, I have something similar. I can make it slightly bigger so you see it in the back. I have two random inputs. I choose a random name and a random process identifier for the state. But now I have preconditions telling me that, well, there should be processes in the state, otherwise the precondition doesn't hold. So I should take something that exists, otherwise I have a meaningless test case. And above all, the name should not be already registered, because I know that if I register two different processes with the same name, then things are going to blow up. So that should not happen in this case. Okay, so there's a precondition saying the name should not already have been registered, then I can do this. That makes sure that there are less test cases generated, and test cases with the same name registering twice are not generated. And then I have the actual call to Erlang register, and then the next state is that I update my internal state data by the name and the PID that I have just registered. That's all I have to do. So now I have my register, which was slightly more complex than the spawn because I have a precondition on it. You cannot just do it whenever you want. And then there's a whereas, and the whereas has a random argument, which I randomly generate from the name, and then I have the Erlang whereas as the function that I call, and I have no next state function because whereas should not change the state of my system, hopefully, right? So there's no next state function, but there's a post condition. If the name is actually registered, then I should get the PID back, otherwise I should get undefined back. That's my post condition on the function whereas. The register function did not have a post condition. If you look into the specification, the register function just returns true. Okay, so there is no post condition needed there. With this kind of little state machine, because this is a state machine updating the state, I can generate the test cases that you've seen on the screen. So you get those kind of tests generated. So that's nice. Now I have to execute those and then see that the post conditions actually hold. And that's what is done in the property. That's why it is also called property-based testing. So here I had the function tests, which gives me the tests. It's just a sample of the commands that I can generate. I can use the same commands, not to generate, say, for all the commands that I can generate, if I clean up the system first, because I have to kind of unregister everything that's there, if I make sure I have a clean-up system, I run the commands, then the result of the commands should be okay. And if not, I pretty print the commands in a nice way. So that's the whole state machine that I need for this. It gives me those test cases, and now I can also run those test cases. So I call QuickCheck with the name of the property. With the property. So this is on the bottom of the screen. I can probably get that higher up. Yep. So I run QuickCheck with this works better. Yes, that works better. With the property as an argument. So now it's just running all those tests that it generates and will, by default, generate 100 tests. Poof. Something went wrong. Something went wrong. I computed this test case, a whereas, a spawn, another whereas, another spawn, two registers and a spawn, and that didn't work. Okay, that test case failed. Why? Well, here we see what is actually happening when I'm executing this test case. I asked where is C, and the system says, oh, that's undefined. That's fine, right? It is undefined. We never defined it. We spawned the process. We asked where B was. B was also undefined. We spawned another process. Then we registered this process under the name D, and we registered the next process under the name C, and then it said Erlang bad arg. Oh, sorry, we registered the same process with a different name. Yeah. Now, this is a very reasonable thing to debug because it's a relatively short sequence, but you can imagine that in real life you have those very, very long sequences, and then it's getting harder to debug. So what QuickCheck does for you, after that it reports that this test case went wrong, etc., something happened, it starts shrinking the test case. And that you see here, shrinking. So it takes that test case, it's symbolic, you can just throw away things from the test case and see if a smaller test case also fails. And it does that automatically, so you get, after a number of times, you get actually the minimum test case for this error, saying I spawn a process, and then I register that process under two different names. And here you see it in reality. So it automatically gets you to the smallest test case, which is nice if you have to do debugging, because if you have 150 commands and you have to do the debugging, then it takes you some time that you can spend much better with your family. So this is what you get from QuickCheck. And this is what we use in testing TCPIP. Questions about this part? So we make a state machine in Erlang-like language. That state machine is used to generate automatically all kind of test cases that should be valid, and then we run that. I could just, let me see. Yes, I could actually fix the bug, and then you can see that the bug in the model in this case. Because what I did is I register two processes under the same name.
Let's say we have found this condition.
Yeah.
And we agree that it matches our documentation. We like
Exactly. So how do we fix that?
how we fix the test to not
Right. So now we want to update the model. Say, yeah, oh, right, we forgot about this case. You cannot have aliases for one process, right? If you have the same process, cannot have two different names. That's correct. So we filter out that kind of testing. We don't generate test cases where we do this. So we write here some Erlang and also. So you don't want the PIT to already be in the registered processes. Yeah? So I have this tuple in my state with the name and the process. And if the process is already registered, I don't want to register again under a different name. Yeah? So that clause I add here. So now I have added that. Then I have to recompile my module. Ah, well spotted. Where did I forget the underscore? Ah, thank you, yep. So I recompile, and I do a recheck or a check. So instead of QuickCheck, I run check. I hope this still works. Yes, it works. And it now says, okay, this was the smallest test case that you had before. I can scroll it up a little bit. Wait, just a second. I scroll this up. So I recompiled. Then I did a check instead of a quick check, keeping the memory of the latest failing test case. And it says, okay, this test case failed. I execute it now. But when I came here, the precondition failed. I should never have done this because you had a precondition excluding this from happening. So you said precondition failed. So this test case will not be generated next time. So now let's just generate new test cases then. So here we are. And now I passed 101 tests. It was slightly faster than anticipated, so it took one more. So 101 tests it executed. 101 sequences of all kind of calls to spawn, register, and where is, and that's done. And you see it's pretty fast if it doesn't fail. Then you put in your post condition, the precondition you put in your post and say, by the way, you may do an exception in this case, and then you have to catch the register as well. Yes, that's just a kind of shift of thinking, then you put it in your post condition. Yeah. Okay, so that's how this QuickCheck works. Back to the slides. So we need to test all kind of different scenarios in TCP. We had this complex state machine. We need to test all the different scenarios. But as you probably noticed, that the API doesn't really steer the scenarios because the API is too limited to actually get everywhere. And we had this race condition problem. So we both use QuickCheck to generate test cases, but we also use Pulse. And Pulse is part of the QuickCheck package, which says, well, you can also generate random schedules, wild schedules, but random, to test for concurrency errors. And we take full control over the scheduler when we do so, such that it is reproducible to run such a random schedule. But that's also something we use. So the traditional kind of QuickCheck approach, if you can talk about traditional QuickCheck approach after 10 years in business, then the traditional QuickCheck approach would be, okay, let's take the tester. Here you have your QuickCheck model of the TCP stack, this state machine model, which generates test cases that both send something to your normal IP stack, going all the way down, coming to your TCP stack that you want to test, and send something up And before you probably send something, you send a message here saying, hey, I expect this TCP stack to come up with this message. Or you say, well, by the way, send something to the TCP stack here, then it is actually sent down here, and then it gets up here, gets up there, and you compare it. So you compare basically the model via a real IP stack, because you don't want to encode all the Ethernet frames and all that stuff, and you decode all the Ethernet frames, etc., and then you come back up here. That's the kind of more traditional approach. That's also how you would normally test your TCP stack against some kind of Linux stack that is well tested. You say, oh, we do the same. Just try to do all that. And that's kind of system level testing almost, right? Because it's very good for for doing this on system level. You have the whole stack with all the IP and the packaging and the encoding and decoding in that test case. So it's very good for finding incompatibilities, but it's not so good for actually hitting those special cases that you want to hit. So it's not very good for kind of fault injection, because you can't really fault inject. Well, you can, because then you have to open this Ethernet frame, and then you have to do some things there from QuickCheck and steer that. So that's a bit tricky. So we don't want to do it in that way. And if you look at the state machine, then it will be clear how we handle that. So this is a state machine again. So how did we make the state machine for TCP/IP? And the state machine, if you can't read it now or don't catch up all the time, it's in the Git repository that I will show in a moment, right? So you can read up on it later on. So how do we make the state machine? Well, we have one kind of operation here, a passive open, making a listen socket. So let's put that into a state machine. So what does the state machine look like? It has some arguments, and that's a port. You always create, on a random port, you start a listener. So there's a port number. There's a precondition that the port should not be in use, because you cannot have two listeners on the same port, on the same IP address. Listening to the port is calling the actual implementation, TCP connect listen, user listen. That's my actual implementation, so that's what I should do. And then as a next state function, adding this to the state, where I say, well, the state has an IP number, it has a port number, it has a socket that it got back from this listen thing. You get a socket back, basically. So I put that socket in my state. And then my next state here, well, I add this to the new socket. So I've created a socket by doing this. So that's my specification of the listen. Now, what's the next thing you could do? Well, you could write a specification of this open. But as soon as you do that, right, if you write this of the open, then it's starting and sending a send, and then this will immediately go here and send a SYNAC, and you immediately go here, and you are in established. And the problem is, if you do that, you will never be sure that you can stay there and tune the system. So you cannot kind of test closing it in the SYN received unless you try to enforce that with an exit at exactly the right time or whatsoever. Very hard to do. So that you can't do. So instead, we use the following approach. We said, no, let's take full control over this. Can we kind of have an API to receive the SYN message here? That would be nicer. So if we can do that in our state machine, then we can steer very, very carefully. So that's what we do here. We have a SYN precondition that we have to have a socket, and then we have a random argument that someone in the network is sending us the SYN message. And now I don't care about whether that really exists or not, but someone is sending us a SYN message, right? So that's what is happening here. I generate a SYN message. And then when I do the real SYN, I have a TCP received here in the bottom that's actually executed, and that's part of that package that we test. So there is a receive module that receives IP numbers, and that's the one that we actually call when we got the received message. So this is the SYN message. And the next state then would be that we update and say, well, in the next state we are in SYN received and we wait for the next thing. But what about the sending here? How can we test that we actually also send as soon as we receive the message? Because that's what the implementation has to do. We should not send it. As soon as we receive this message, it should send a message, right? Now we come into mocking. We want to mock this behavior, okay? So how do we do that mocking? Well, we designed a special language for describing the mocking behavior, because mocking is not as simple in randomly generated tests as in kind of manually written tests. Because in a manually written test, you know what's going to happen, so you can encode that. But if the system is generating a test, it also has to generate the mocking and has to be compatible. So this is, what happens in the mocking. We say there must be a call-out. A call-out is the system should do something. What should the system do? Well, it should spawn a new process. We should be able to observe that. This new process has a new ID. I set some variables there. It gives me a new socket. And then I have to see a send, right? There should be a send, and I get a packet back. And actually, I can inspect the packet, and I can check that the packet fulfills certain criteria, that this packet indeed contains a SYN and an ACK, which is written here. Yeah? So you can just encode that in your language, and okay, this is a bit of too much code to just throw at you, but the main point here is that this code is, with some kind of training, readable, as well, looks almost like Erlang code, and this is understandable if you know the specification. So you can map this one immediately to the specification. You can say, oh, this is indeed implementing the spec. You actually are waiting for a SYN ACK here, and you're actually spawning a socket here, and that's what's happening here. So you can manually inspect that you implemented the spec in the right way. So the QuickCheck model is a specification of that diagram. So that's what we did. We wrote a specification of that diagram, and we automatically generate tests to see whether this Erlang TCP follows the specification. The QuickCheck model is rather general. So we can use this for any TCP stack in principle, where we have those kind of API functions that we need. But we can now also fault inject in any possible place. And that's very useful. So we can not send the SYN, or we can close it at stages where we could hardly close it before. And we did that, of course. And then we found a number of errors. So the work was divided as follows. We at QuickCheck would do the testing, and Otolonetworks would then fix the bugs. And that's, I think you need a kind of separation, because whenever we proposed a bug fix, Rick came back to say, nah, I would do it differently. And he's a TCP expert, so better let him do the different fix then. We were kind of taking some shortcuts there. We probably would be bad for performance or other things. So he fixes the bugs, we test. And one of the bugs we found after shrinking was this kind of race condition. And a nice way of using Pulse for this is you run your system under a schedule that you provide, and then it shrinks also the schedule to the minimum number of context switches needed. So the error we found was we start a listen process, we get a SYN ACK back, we send an ACK, and then the system hangs. And only 1 out of 100,000 times it's actually hanging there, if you do not run it with Pulse. And with Pulse you can reproduce that. So that then goes to the poor guy in the Pacific Ocean in his boat and says, look, there's a problem. And he's sitting there with his kind of little network inside the boat and fiddling out and writing some new code. So that's how we work together. There's a bit of delay because of time differences as well as kind of satellite communication, but it worked fine. And then he fixed this error, for example, and this is now in his repro. So if you want to contribute, this is his repo. Look in there and write your additions to it. He's very happy to take things into his stack. Other things we found, just to give you a feeling of what you can do with that, is you open a local thing and then never sending a SYN at all to the remote port if you local opening. So that's also something which happened very, very rarely, and which was, I don't exactly know why it was, but it was kind of very strange to see this happen so seldomly. Had to do something with the packet size, I think, or the IP address matching exactly something else or whatever. When something is established and you close at the same time, the one that I showed in the beginning, both want to terminate the connection, both send an acknowledgement, then one of the, this is the local, was actually hanging and the close never returned. So you did a close and it was just staying there until the timer would say, hey, I tried to close, but they never got there, even though you got an acknowledgement and you should have closed. So that is the kind of things we pick. And we would be able to see that because of QuickCheck, but also because of the instrumentation with Pulse. So Pulse is for standard Erlang programs. So you can also use it for Elixir, but it's really kind of connected to Erlang, because we take control over the Erlang scheduler. We instrument your code, and we use Pulse to generate non-deterministic but random schedules, and we can then rerun the schedule in the same way as we did it before, and that makes it nice to shrink race conditions. Okay, so that's where Pulse comes in, and just simply how this is done is you have your Erlang program, you compile with the parse transformation, and that instruments all the spawns, the links, the sends, the receives, and all the stuff, and it will be under control of our own scheduler. So we control the concurrency, and we switch, and we try to minimize the switching. Okay, to conclude, I'm faster than I had expected, but to conclude this talk then, I can say that using QuickCheck and Pulse have shown to be very effective in finding those really tricky errors that you can have in this mega asynchronous system that TCP actually is. And what is up next is that, okay, the bugs that are still left or might be left there are being fixed by Ricky. And then we do, he is working on MD5 checksums as one of the additions to the TCPIP protocol, where you can put a checksum on the packet, which is an interesting thing to do. And we will try to test that, I guess, as well. And then you can contribute with your own extensions to TCPIP, and we hope that this is a kind of a project that keeps alive a long time, and where we can, what we can use as a showcase of how to test complex state machine software, and what you can use as a nice user-level TCP implementation. Questions?
Ample time for
Hi there, thank you. Very interesting talk. Regarding Pulse, that sounds very cool. Is that open source software, or
No.
is that proprietary?
That's proprietary software.
Okay. So I have to write my own one if I want.
Or you just buy it, that's fine. It depends on how you value your time.
I have a second question, if that's okay. You mentioned something about you found a race condition or something where like 1 in every 100,000 you wouldn't get a SIM back, and it was something to do with the packet size or whatever. So the packet size and content sounds like something you could also
That's randomly.
QuickCheck.
Yeah.
So is that easily combined? Like you've got this one thing that you've shown us about the state machine for TCP, and presumably another thing for randomly generating the content of messages.
It's in the same model. It's only a few lines where we randomly generate the content of the TCP message.
Okay, so those combine quite easily.
It's combined.
Okay,
very
great.
easily,
That's
yes,
cool.
yeah.
Cool. Thank you.
More questions?
Hello. Question is QuickCheck used in higher level testing of systems? Let's say more like web API level, or on higher level protocols. Is it used that way, and is it feasible to use it?
So the question is, I guess, is it used for larger systems as well as just kind of
Yes.
things that you could probably imagine to write auto tests for? Yes, it is. For example, we have tested the car software in the Volvo, so the whole ECU level testing. So not the whole software, but at least part of the operating system is tested in this way. You can also use it on the top level of a web service, where you just do HTTP requests and test on that level. So you can choose which level you want to test it. It's actually beneficial sometimes to be on a higher level if you're not interested in encoding all the details of what should happen in the bottom. React is another example. For example, we tested on the complete system and not on all the different modules.
Well, if there are no more questions, I suggest that we thank the speaker and remember to provide feedback.